Alright, so in this lesson, we're going to be talking about inverse functions. We're going to find inverse of functions, determine if they are inverses of each other. We're going to use the graphs to show if they are inverses. We're going to use something called the horizontal line test, which is a little bit different, but yet a lot like the vertical line test, which we are already accustomed to. But it's going to help us tell us something about functions and their inverses, if in fact there is such a thing. First thing we want to take a look at is, let's say that f of x is equal to x plus 4. And let's say the input values we are given are 1, 2, 3, and 4. Keep it simple. What output values do we get in return? Well, 1 plus 4, so 1 plus 4, 2 plus 4, 3 plus 4, and 4 plus 4. That is, f of x plus 4 is equal to those ordered pairs according to the given input values of 1, 2, 3, 4. An inverse function of f, denoted by f inverse, so the -1 exponent doesn't, it's not really an exponent, it's like almost again like a label that indicates that here we're talking about the inverse of function f of x. So when we see f -1, we're meaning the inverse function, and we find that by switching x and y values together. So f inverse, so the inverse of this function x plus 4 with the given points 1, 5, 2, 6, 3, 7, 4, 8, simply switch x's and y's and we get 5, 1, 6, 2, 7, 3, and then 8, 4. So the inverse of each one of those, you notice, is created by, well, instead of x plus 4, now I can just take and say, okay, 5, if I subtract 4, I get 1. 6 minus 4 is 2. 7 minus 4 is, okay, so it's got a pattern. It's got an equation. That equation for the inverse is, in fact, x minus 4. Well, this is a pretty simple equation where instead of adding 4, I do the inverse operation and subtract 4. There's a method to that, and there's a reason why that works that way. But just for now, know that, well, I just switch x's and y's, and in this case, instead of adding 4, I'm going to subtract 4 to get my values. That is, if any point is, in fact, part of a function, if a point is within a function, then such as, a comma b, or 5 comma 3, or -6 comma 2, doesn't matter what those points are. If it is a point within a function, then b comma a, the reverse order, switch x's and y's around, would be in the inverse of that same function. Now, the composition of f and its inverse, or of the inverse and a function, has the effect of undoing what the other one has done. Just like we saw a second ago, instead of adding 4, let me subtract 4. And what that does, it gives you the identity function. The identity function, if you remember, was one of our parent functions. And so when I do the composition of f inverse of x, I'm going to plug in the inverse every time I saw an x in the f of x equation, and then I add 4. Well, plus 4 minus 4 cancels, gives me x, like we said, the identity function. Likewise, if I take the inverse of a function, so inverse of f of x, so when I do the composition of f inverse of f of x, I find out that I'm going to substitute x plus 4 every time I saw an x in the inverse, and then subtract 4 when I'm done. And same reason, 4 minus 4 will cancel. I get just x. So what that tells us and helps us identify is the actual definition of an inverse. We talked about switching x's and y's, but the inverse of a function, as it will undo what another function does, for example, squaring and square root, multiplying, dividing, all those kind of things. The definition of an inverse is if f inverse is the inverse function of f, then by doing the composition of those two, Whether you do f of f inverse or reverse that order and say f inverse of f of x, the result should be x either way. Whatever one does, the other one will undo. And you just go back to the input variable, which is x. So at this time, let's go ahead and see and check if functions are in fact inverses of each other. There are three functions. Two of these are going to be inverses of each other. The question is, which two? Now, if you're looking just in terms of inverse when it comes to just operations, you might be able to tell which ones are going to work. One looks a little bit weird. One doesn't look as nice as the other ones. For that matter, two of them are actually fractions. So I don't know, maybe they don't stand out as much as I thought. But the idea is this. I take one function and I'm going to substitute into any of the other ones just to simply find out what happens when I do the composition of these two. So if I take g of x and I'm going to replace g of x into the f of x equation, that is, I'm going to find f of g of x, or fog. I'm going to take f of x, the equation x minus 4 divided by 7, every time I saw an x. And so notice right here, so let's say f of x is x minus 4 and then divided by 7. And then g of x is 7x plus 4. Every time you see an x, you're going to substitute with the g of x equation. So notice, let's color code here so we can make these things stand out. This was the x value for f of x. The blue that remains was the f of x equation. In place of x, though, I said put g of x there. Composition of functions means an entire expression replaces x in the other. Let's see what happens when we do that. Well, 7x plus 4 minus 4, I really don't need the parentheses there. Ends up, the 4's will cancel, gives me 7x over x. And 7 divided by 7 is x. So right off the bat, I found out that f of x and g of x were in fact inverses of each other. And how do I know they were inverses? Is because after the composition of f of g of x, my final answer was just x, the identity function. Let's take a look at what happens here when we talk about f of h of x. Well, same thing. Let's go orange. So the same thing this time, except that where I saw an x, I'm going to replace that with g of x this time. So g of x is going to go into the f of x equation to replace only the x value. So here's all the things that are blue that's still part of f of x. And now h of x, which is the orange color, x minus 4 is going to go into the equation. Now, minus 4 and then 7 over x minus 4, nothing's going to cancel nicely there. Best thing I could do is that. And then separate that with minus 4 over 7, which is, in fact, not anything nice. Simplify that if you want, but you know right away, if it doesn't clean up nicely or easily in any way, probably not going to get you to x. Probably not going to be an inverse. For that matter, it is not at all an inverse here. So these two, did not mean to move that. So these two here, f of x and h of x, are not inverses. And you can even try that with g of x, and you'll find out it's the same case. G of x and h of x will not be inverses of each other, because we already know that f of x and g of x were. When we did the composition of those two, we got back to just x. We can also verify inverses if we simply graph an equation. The graph of a function and its inverse will be symmetric, and WRT is not a typo, and it is not WRT, It is with respect to, so WRT is just an abbreviation for with respect to the line y equals x. That is the identity function, y equals x. That means you should get an exact mirror copy on both sides of that line. So a point A comma B has an exact location in that line B comma A. It is a line going right down the middle diagonally that links, basically becomes the mirror of the function and its inverse. Alright, so it is symmetric about the line y equals x. So it's a split right down the middle of the graph for the mirror image, as opposed to the previous symmetry lines that we've talked about, which is the y-axis, the x-axis, and we've even talked about origin symmetry. So let's verify that both of these graphs are inverses of each other. So we know right now they are, but we want to verify these either algebraically or graphically. Does not matter. So what I want you to do is that I want you to take a second and try to graph these on your own. So pause the video, try to graph these and see the result that you get. If you need to use Desmos to assist you in graphing, that's fine. You can also use a table of values. And then we're going to take a look at those two results. Alright, so pause the video. Now let's take a look at the answer. So y equals 2x minus 3. What does that one look like? Well, if you make a table of values, that's perfectly fine. Just do that. And we're going to say for this one, I'm going to make a table of values for x and y. No real limitations to this. -2, -1, 0, 1, and 2. There's no need to pick any other numbers. So 2 times -2, -4, minus 3 is -7. So -2, -5. So 0, -3. 1 is going to be -1. And then 2 is going to be +1. So that's this graph. Now when I pick this next set of numbers, let's go ahead and say x. Let's say y. I'm not going to pick the same values because if I do, it's not going to work out nicely. However, a couple of strategic things we can do here. Let's just say that we have no idea these are inverses or not, so let's just pick some random numbers anyway. I probably don't want to pick -2 because that's going to make this an odd number. I have to multiply by 1/2. So I probably only want odd values. So let's do -3. -3 plus 3 is 0. Half of that is 0. So let's go -1. -1 plus 3 is 2. Half of 2 is 1. +1 is 4. Half of 4 is 2. And likewise, if I take +3 plus 3 is 6. Half of that is 3. So I strategically picked points that I can take half of after adding 3 to it, meaning I just had to look at some odd numbers. But there's something you will notice right away in these equations. Remember, inverses have f of x with some value a comma b. That means the inverse, f inverse, will have the same value b comma a. It looks like they're just inverted values. So 0, -3 becomes -3, 0. 1, -1 becomes -1, 1. Even 2, 1 is 1, 2. So it's looking like they are going to be inverses simply from a table perspective, but when we graph it, we verify that they are. And how do I know these are inverses? Well, remember, this would be symmetric with respect to the line y equals x. That is our identity function. How does that look like on a graph? Well, it goes right down the middle of these two graphs. And if you were to graph the line y equals x, you will see that it will split the graph perfectly in half. So let's try to do that. Kind of missed a little bit, but we can fix that. Let's move that line. That line just needs to go up a little bit. Maybe right there. Close enough. Again, it's a little crooked, but it is what it is. So it is symmetric about that line. There's a mirror image, a copy of this graph. Let's see if we can do that better. I think we can. The problem is this is a print or a screenshot of a TI calculator that we know is not a perfect square to begin with. The TI calculator is slightly, I guess, widescreen. Same thing with number 2. You can do the same thing with table of values. If you want to do that, that's great. X squared, they're telling you to keep x's greater than 0. There's a reason for that, because the inverse of that has to be the square root of x. But for it to be a function, we have to restrict the domain. Also, because I can't use negative values in my square root. So restrict your domain to only positive values greater than 0. For that matter, it doesn't have to be greater than 0. Greater than or equal to 0 will work. So here we say x, we say y. So 0, 1, 2, even 3 if you want. Square it 0, square it 1, square is 4. All right, so for the square root, again, I can only use my input values to be positive numbers. So I can say square root of 0 is 0, square root of 1 is 1, but I can't do the square root of 2. The next number I can do the square root of is 4, and that's equal to 2. And if you notice from the table of values, the same thing is happening here. And 0, 0, you're not going to see it. 1, 1, you're not going to see it. But you clearly see a comma b and b comma a under 2, 4, and 4, 2. The graph looks like that. It is only in the first quadrant for a reason. Again, we are not allowed to have negatives instead of a square root, so we just have to restrict the domain. And if we draw the line y equals x, it is symmetric. And we see that it splits the graph right down the middle.